She is a life member of Indian Science Congress. He has submitted her PhD thesis to Resident University. She has published 25 research papers.
Good evening, everybody. And my research work entitled, I'm going to present that is media optimization in immobilized culture to enhance the content of curcumin in Curcuma longa and protein profile of treated samples in static cultures. My experimental plant is Curcuma longa that belongs to family Zingiberaceae of monocot. Due to the increase in the population, there is a need of for the alternative mean for production of secondary metabolites. So we have used as a alternative mean plant tissue culture technique for the production of secondary metabolites. That is the bioactive principle of Curcuma longa is curcumin, that we have enhanced the compound. Common name of the Curcuma longa is having a miracle stem and is having so many medicinal value like anti-arthritis, skin tonic, speed of wound healing, natural analgesic, natural anti-inflammatory activity, lower cholesterol, prevent many cancers, activity, etc. So the phytoconstituents of the turmeric are, the main component of the turmeric are curcuminoid and essential oil. The natural curcumin from Curcuma longa contain curcumin number 1 4.8%, curcumin number 2 6%, and curcumin number 3 is this around 0.3%. Apart from these, there are other components like moisture less than 9%, exogenous matter that is less than 0.5%, volatile oil that is less than 3.5%, and sesquiterpene, etc. The aroma of the turmeric due to the turmeron and gingiberon has been observed. So my goal is for curcumin, that is for enhancement of the production. So this can be stable in the enol form as well as in keto form, where enol form is more stable in soluble as well as in solid forms. So these are known as the tautomeric form of the curcumin. This is the phenylpropanide biosynthetic pathway of the curcumin. You can see over here the starting point is phenylalanine, from which the curcumin biosynthesis is taking place, and after cinnamic acid, comeric acid, ferulic acid, ultimately the curcumin production is taking place. Here the PAL, that is phenylammonia ligase activity, is occurred on the phenylalanine, and afterwards the curcumin synthase is activated for the production of curcumin. Behind the production of the curcumin, there are two different biosynthesis mechanism when two molecules of the cinnamic acid extendedly joined with in the presence of melanine coenzyme A, the production of curcumin is taking place. So two other derivatives, that is bis-dis-methoxycurcumin and dis-methoxycurcumin, is observed apart from curcumin. The production site of the curcumin is around is a leaf cell, and where the leaf in the leaf only the starting point is the sucrose in the cytoplasm, where it then transfers through the plastid, that is chloroplast, where the shikimic acid pathway is taking place, and this produced chlorosmate is then transferred to the cytoplasm, where phenylalanine is produced finally. The produced phenylalanine then transferred to the endoplasmic reticulum, where the phenylpropanide biosynthetic biosynthetic pathway is taking place, and the production of the polyphenol, that is curcumin, is taking place. And this produced polyphenol curcumin is then accumulated in the semi-epidermal cell and epidermis part of the cell, and then it translocates to the rhizome, which is the accumulation site of the curcumin. These are the other sources apart from Curcuma longa of curcumin. This is the medicinal use of the curcumin, like in chronic diseases, in infectious diseases, in inflammatory diseases, and others. So advantage of plant tissue culture for secondary metabolite production. This provides the system for the production and biosynthesis of the secondary metabolite and biotransformation, then regulation of the metabolite synthesis. Like If we want to get and enhance the compound that is our interest, that are of interest, so that may be occur because by the using of different strategies in the plant tissue culture technique, that is by using abiotic stress, that is by biotic stress, by using phytohormones, growth regulators, by genetic engineering, and by hairy root culture, by these some techniques that we can use, and by modification of the environmental condition we can also produce and enhance the compound of interest in our laboratory. It is independent of seasonal and geographical variation, as it is used in the control condition, that is 25 to 27 degree of temperature, 1000 lux of light, and for 16 hours of light and 8 hours of dark period, and 70% of humidity. So that's why we can say this is the seasonal and geographical independent variation independent technique. So this is a continuous reliable source of plant pharmaceutical and could be used for the large scale culture of the plant cell for secondary metabolite production, as any of the plant cell has a totipotent in nature, means the plant cell have a capability to produce the secondary metabolite that can produce by the mother plant. So this characteristic feature of the plant cell we have exploited by using the plant tissue culture technique. In the present study, dual strategy were used to enhance curcumin in Curcuma longa. Dual strategy means first we have to produce the biomass in the production in the growth media and then transfer to the production media. So this was used first of all by Zenk 1975 for the admolacine production in Catharanthus roseus. So we have used Zenk media as the production media in the present study in static as well as in immobilized culture. So two different range of tyrosine and cinnamic acid concentration was selected by observing the toxicity of this compound on the plant cell. So the objective of present study is to develop a novel economical potential method for enhancement the curcumin content in vitro tissue culture, static and immobilized culture of Curcuma longa, and to evaluate the protein profile of treated sample in vitro. So material method, plant material of Curcuma longa rhizome was collected from local market. In the month of March, the identification was done by botanist, Haffkine Institute, and the voucher specimen of Curcuma longa preserved for reference. The static culture was developed by using the surfaceization in 0.1% of mercury chloride for 3 minutes, and afterwards 5 times washed with sterile water. The cut pieces of 1 centimeter long, and the inoculation was done in the sterile media aseptically. The inoculation was done into autoclave Zenk production media that was supplemented with different concentration of tyrosine and cinnamic acid separately. The cultures were incubated in 16 hours of photo period and 8 hours of dark period with 70% humidity and 1000 lux of light. The cultures were harvested separately at the time interval for 1 week. The cold extraction in ethanol dried, weighed and subjected for HPTLC analysis, that means high performance thin layer chromatographic analysis, with the standard compound of curcumin that was purchased from Sigma, and the inert gas was used as a spray gas, and chloroform methanol 9:1 was used as a mobile phase. The RF value was observed that was corresponding with that of the standard compound of the curcumin 0.52. The immobilized culture of the Curcuma longa was created by using the 2% of calcium chloride and 50 micromole of the sodium alginate. The calcium alginate entrapped cell were kept in the Zenk suspension media, supplemented with 40 mg and 60 mg of the tyrosine and 5 and 7.5 mg per 100 ml of the cinnamic acid separately. All the cultures were kept in all 90 rpm and 25 degrees centigrade for 1 week duration. 1 week old sample were harvested, extracted in ethanol and centrifuge. The supernatant of centrifuge extract were dried, weighed and subjected to HPTLC analysis for qualitative as well as quantitative estimation of curcumin content. And the protein profile studies was carried out by using protein extraction by kit method that was purchased from peers. The protein profiling of extracted protein was done by using 1D SDS page. The static culture, you can see over here the 1 centimeter long around plant tissue of rhizome of Curcuma longa was inoculated aseptically on 0.8% of the agar media. So that was the production media. The preparation of the beads, that was done by using sodium alginate and calcium chloride. This is the immobilized culture of the Curcuma longa. Results. 7-fold enhancement in curcumin content was observed in 1 week old static culture, which was maintained on Zenk production media incorporated with 5 mg per 100 ml of the cinnamic acid. That was higher than other samples which were used. In immobilized culture studies, curcumin content was higher in 1 week old immobilized suspension culture supplemented with Zenk vessel media in 5 mg per 100 ml of the cinnamic acid, which was higher than other samples. In protein profile studies, all the treated samples were analyzed for the proteomic profile using 1D SDS page, and it was observed that protein of 23420 Dalton was most prominent in all samples. In Curcuma comosa, it was observed that the 23420 around kilo Dalton protein was observed, that is maybe glycine rich protein. That was reported in the Curcuma comosa. So we hypothesize here only this protein may be of glycine rich protein, which acts as a defense mechanism. Ultimately the production of the curcumin is maximized. So the maximum intensity is expressed in tissue grown in tyrosine 40 mg per 100 ml. This is the HPTLC chromatogram of immobilized culture at 425 nm with the standard compound of the curcumin. And this is the HPTLC chromatogram of bioenhancement of the curcumin in Curcuma longa static culture. This is a fingerprinting of the plate of HPTLC, in which you can observe that the in middle part this is the curcumin standard, and number 1 is for 5 mg the sample that treated with 5 mg per 100 ml of the cinnamic acid, and whereas number 5 is for control, number 1 is for the sample treated with 5 mg per 100 ml cinnamic acid. The prominent spot was observed in the number 1 as compared to the other, which says that it is maximize the concentration of the curcumin in this sample. The table showing the enhanced curcumin content of the Curcuma longa in static culture as well as in immobilized culture, where the 8.71% was observed in the static, whereas it was 2.03% per 300 beats observed in the cinnamic acid that was fed with cinnamic acid 5 mg per 100 ml. All the treated sample results were statistically significant, and that was done by using the ANOVA test of 3 duplicates. The curcumin percent in immobilized culture, the curcumin percent in static culture. This is the protein profile of induced sample, that is tyrosine 60 mg per 100 ml, tyrosine 40 mg per 100 ml, cinnamic acid 7.5 mg per 100 ml, that is 2 and 3 and 4 respectively, whereas 1 for ladder and number 5 is for control. The sample that was fed with 5 mg per 100 ml of the cinnamic acid did not show any of the result. That may be because of the ROS formation due to the osmotic stress or abayotic stress that has been given in these studies. We have used 5% of the sucrose, which known as a abayotic stress or osmotic stress that create the ROS formation, and ultimately the modification of the protein occur, and that's why we can say that that reduce the protein content. And other thing, that cinnamic acid has a pKa value around 4.4, and whereas tyrosine is around 10. So pKa value is inversely proportional to the strong acid. So that's why we can say the strong acid is cinnamic acid other than tyrosine. So that's why that modify the protein, and so here we can say the modification of protein can occur. So this is the relative band intensity. You can see over here 65.53% in tyrosine, that was 40 mg per 100 ml. This is the comparison between the two strategies that we have used. Here we have used, in the present study, we have used directly plant material from outside and then used for the study for the production of the curcumin in vitro condition. But in the previous condition, where we have to first develop the callus, for that is taking place for the 6 months, and that expenditure was maximized. But in the present study, we have reduced expenditure as well as time for the production of the curcumin. So that's why this is saving of the USD around 1235, that is 92%. So that's why this present technique is very economically efficient and novel. The discussion. Cinnamic acid and tyrosine compound are intermediate compound in biosynthetic pathway of the curcumin. It can be observed by this study. And the secondary metabolite in cell culture have been enhanced by many scientists by following these strategies. The expression of protein based on intensity of the band was reduced in treated sample as compared to the control. This may be due to the formation of reactive oxygen species ROS in culture condition, and which modify the protein, that is pK value cinnamic acid 4.4 and tyrosine is 10. So accordingly the protein is reduced. The increased level of sucrose, that MS media, that is 5%, MS media we have used 3% for the callus production and the curcumin production in another experiment, but in the present study we have used 5%, that create a osmotic stress and abiotic stress. That's why the abiotic ROS formation is occur, and ultimately the production of the curcumin induced. Accumulation of compound depends upon so many factors like amplitude of the pH, this was observed in one experiment when NaCl treatment is given to the ajmalacine for the production, ajmalacine production in Catharanthus roseus. It was observed that the ajmalacine production decreased. So that's why pH is very important. Difference in the pH is very important. Permeability coefficient at the tonoplast, because the vacuole is the accumulation site for the storage of the secondary metabolite in the cell. Because there is so many compartments for the production of the secondary metabolite in the cell, so that's why the permeability of the tonoplast is very important factor for the production of the and accumulation of the compound. This pK value, again, this pK value is very important. Binding site in the vacuole, there are different binding site in the vacuole inside the vacuole, like magnesium ion for the citrate and phenols for the alkaloids. So this binding site is very important for the accumulation of the compound. Specific carrier very much required for the translocation of the compound from the production site to the accumulation site. So development of the organs, tissue and cell. As plant cell having three different phases, like log, lag and exponential phase. So exponential is for the production of secondary metabolite, whereas the log and lag for the preparing mode of the phase. So that's why this development of the organ, tissue and cell factor is very important, and thus ultimately the size of vacuole, when the size of the vacuole is small, the small accumulation, and the higher then higher. So this is the, again when we have given the stress, that may be abiotic stress, that may be osmotic stress through the sample of the in culture, then ROS formation occur and stress signal transduction is carried out, and ultimately the PL activity induced, which is the key factor of the production of curcumin in the present study. This the proposed biosynthetic pathway of the curcumin, where we have used tyrosine and cinnamic acid. These are interrelated together. The significance outcomes: static culture is better source than immobilized culture for curcumin production in vitro tissue culture of Curcuma longa. Zenk media incorporated with 5 mg per 100 ml of the cinnamic acid phase with 5% sucrose is the best media for curcumin production, that is abiotic stress or osmotic stress. Created ROS in vitro condition can reduce the protein profile in treated sample. Glycine rich protein may have role in curcumin production in tissue culture. Study made easy to understand curcumin biosynthetic pathway, and the present study deals with the enhancement of curcumin using directly plant tissue rather than callus, which save time as well as expenditure. These are the references. The work was done in Haffkine Institute. When the Gandhiji came in 1935 in Haffkine Institute, it message: you must be the change you want to see in the world. The Haffkine Institute is known for the invention of the plague vaccine, first of all. So its message is alleviating human suffering through science and thereby serving the welfare of the people. Thank you for your attention. Any query? Yeah.
Have you considered the genetic side, like gene sequencing side, like you look like the cinnamic acid is a epigenetic modifier, or it may have activated a protein like associated with genetic cluster involving biosynthetic pathway of that metabolite. I think that it needs to be studied like a genetic genomic mining.
Yeah, we are actually going on this kind of work is going on, and the curcumin synthase, we have concentrated on curcumin synthase for the production in the treated samples. So right now we are doing this kind of study for curcumin synthase. That is the key point for the production of curcumin. And
But I see
yeah.
that we can trigger the correct biosynthetic pathway if we come to know about the gene sequencing like genetic mining. So
Just a minute, huh? Yeah, you can see over here that last one, that is curcumin synthase enzyme, works on the production of curcumin, right? So we are actually concentrated on CORS, that is curcumin synthase enzyme, for the production of curcumin molecular level.
So if I understand correctly, you're extracting the curcumin out of the cell, right?
Yeah.
Can you harvest the medium?
No, actually we have extracted the plant material, plant material harvested after 1 week and then extracted for ethanol. That is, ethanol is solvent for soluble. Curcumin is soluble in the ethanol, so that's why we have used ethanol in the room temperature, and then we have analyzed for the production.
can you harvest the media?
Harvest the sample. Harvest the sample.
No, that's not. These alginate beads, as I remember from many years ago that we did it, we had an incubator, and these beads
There is
were
a
floating around in a circulating
Yeah, that
vessel,
is a rotary shaker.
and you could actually filter the beads out and actually extract your product from the medium.
Yeah, we have checked the curcumin content in the suspension culture, that is liquid media, but I didn't get any of the content of the curcumin.
Well, that answers my question.
Yeah.
Thank you.